everyone. This lesson is meant to review what you've learned thus far about series, and the word series really does kind of summarize pretty much everything that you've learned in the last few pages worth of the packet. So it's worth taking a moment as we begin page 13 to remind ourselves that we have technically learned 3 different types of series. The 3 different types of series for which we now have formulas and examples are the types that I recorded notes for on my cover page of my packet, and hopefully you've done the same. We have 3 different types of series that we've seen: the arithmetic series, the finite geometric series, and the infinite geometric series. So those 3 categories, arithmetic, finite geometric, or infinite geometric, are going to be kind of important. Now, it is worth noting that the arithmetic series has only one formula, where geometric is divided into 2 categories, and that's because a geometric series could be infinite or finite, and we have situations where both of those problems are possible. It's not possible to have an infinite arithmetic series because of the nature of an arithmetic series. An arithmetic series is always going to keep getting bigger and bigger and bigger and bigger, whether it's more positive or more negative. So it's not possible to add up an infinite series of arithmetic terms. It's only possible geometrically, and it's only possible to do an infinite geometric in the very specific situation where the numbers are getting smaller and smaller and smaller and smaller and smaller. So that's worth noting as well, that the infinite geometric is the only type of infinite series that you'll see. Sometimes people call the formula that we wrote at the beginning, the Gauss formula, a finite arithmetic series, just to have that symmetry of the titling. So if it helps you to think of it that way, you definitely can. In any case, think of those 3 categories as you're beginning page 13 today. Think about the fact that you have 3 types: finite arithmetic, finite geometric, or infinite geometric, and maybe consider asking yourself, for each of the problems that you see on this page, what type of series best fits the situation. That will tell you which of your 3 formulas you'll need to use, and that should give you some strong guidance about how to do each problem. I'm going to do a series of examples just based on questions that I anticipate people have as they work on their own, but I'll make the disclaimer that I'm not going to make a video for every problem on this page. If you have a question about something that I did not make a video for, the answer key is still available, and you can always pop into the next available office hours to ask me to go over a question if there's something that I haven't yet clarified. As another option, you can always send me an email with a question, and I'll be happy to answer via email if that's easier. Now, the first question I'm going to try is the first one in question number 1. This one's asking me to find the sum of this series. So it's got to be one of these 3 types. It's got to be finite arithmetic, finite geometric, or infinite geometric. Those are the only 3 possible series I have. By the nature of this expression, I can tell this thing looks arithmetic. Instinctively, I can tell it's not geometric because I don't have that power of n, and geometric problems typically have a power of n in their equations, so that's tipping me off that this is probably going to be a finite arithmetic problem. I'm going to write that just so I know that this is finite arithmetic, and so I know which formula I need to refer to. I know I'm going to have to use the finite arithmetic formula, which, if I copy that from my notes, was 1/2 a sub 1 plus a sub n times a sub n minus a sub 1 all over the adder plus 1. So that formula is going to be necessary, and that means I need to extract from this problem all of the necessary elements of the formula. I need to be able to figure out the a sub 1, the first term, a sub n, the last term, the adder, and then I need to be able to plug it all in and simplify. So let's make this happen. Of course, the 1/2 is still 1/2 no matter what, so I'm going to copy that part of the formula right off the bat. Then I have a sub 1 plus a sub n. I need to figure out what a sub 1 and a sub 1n are, so I'm going to do that as a little bit of side work here. If you're not sure what the first term or the last term in a series is, especially when you're in sigma notation, one of the best strategies to find the first term, or really any term, is to just plug in that n value. So at the first term, n is 1. Plug that in, into the actual expression. That's what the expression is there for. It's a quick reference tool. So if I want to find the first term, I can plug 1 into that expression, 5 times 1 minus 1, and I can just get the first term algebraically. 5 times 1 is 5, 5 minus 1 is 4, so the first term must be 4. That tips me off then that in my formula, the first term, a sub 1, is going to be 4. Now I need to do plus a sub n. So a sub n in this context is the last term. According to sigma, the last term is the stopping term, and that's always at the top of sigma, so that 7 needs to be plugged in, and that should tell us the last term in the series. So a sub 7, if you want to think of it that way, is the last term. 5 times 7 minus 1, if I plug into my little formula. 5 times 7 is 35, minus 1 is 34, so that tells me that my last term is 34. Now to finish the formula, I have a sub 1 plus a sub n times the same a sub n, the same last term, minus the same first term I already used, so no need to reinvent the wheel, divided by the adder. Now this is where some context clues are going to be helpful here. Remember the structure of an arithmetic expression? The adder is always the part that is attached to the letter n. So this is telling me that the adder must be 5. And then the formula finishes with plus 1. So it's a little bit ugly, but definitely some scratch work that I can do. This looks pretty doable if I simply just try to write it out. I have 1/2 times 4 plus 34 is 38. Then I do a little bit of mental math. It looks like I have 34 minus 4, which is 30. 30 divided by 5 is 6. 6 plus 1 is 7. Now I can multiply, and you can use a calculator for this, or you can just multiply it all in your head. It's up to you. Half of 38 is 19, and 19 times 7 is 133. So it looks like, according to my formula, the sum of the series is 133. Now, of course, it may be helpful to think about an easy way of checking your answers. The way I always recommend checking answers is to use the answer key, but if you don't have access to the answer key, you can always write out all 7 terms and add them up and see that it adds up to 133. That's probably more tedious. I would recommend the answer key, but that's an option should you want to use it. I'll give you a quick heads up. The second question in number 1 is a bit more of a challenge because it's actually not finite arithmetic, geometric, or infinite geometric. This one is kind of an extra challenge. I'm going to pose it to you as an extra challenge optionally, but if you want to skip that one because it doesn't really fit any of the actual formulas that we've done, it's okay if you skip that one. If you want to try it as a challenge, go for it. And if you don't want to try it as a challenge problem, then just skip it in favor of practicing the 3 main types of series. In the next video, I'm going to skip all the way ahead to question number 4. So in the time between now and the time you start the next video, I recommend that you try question number 2 and question number 3, only because they all kind of go together. They're all finite arithmetic. And I want you to know that going in so that you can practice applying your finite arithmetic formula in each case. Eventually, we'll need to get to the point where we don't say ahead of time whether a problem is finite arithmetic, finite geometric, or infinite geometric, that we have to figure that information out on our own. But for now, I'm okay with telling you. Question number 2 is finite arithmetic, and you can tell it has a very similar structure. Question number 3 is also finite arithmetic. And once you read the question, I think it'll be obvious why you would classify that as an arithmetic series. In the next video, I'll go over question number 4. So try to make sure you're okay with these first 3 problems first, and again, skip the challenge if you want to. And then when you're ready to do so, begin number 4.